Okay, thank you. It feels so nice to be back to HAO again. Reminds me of those days when I was still young. So today I'm going to talk about the flux emergence stuff. I will talk about how we go from large scale to small scale flux emergence in numerical simulations. And on the Sun, we all know that there are a hierarchy of magnetic activities from 11-year cycle of the sunspot number, where the sunspot appear here in the middle latitude and gradually disappears as it approaches the equatorial region, produces this 11-year cycle, and also the sunspot are magnetic concentrations of several kilogauss with magnetic flux up to 10 to the 23rd, 24th Maxwell on the Sun. And there are also small-scale internetwork magnetic fields, together with magnetic eruptions. The picture here is showing you an image of CME eruptions, where they expel a tremendous amount of material and energy into the interplanetary space, causing a phenomenon called space weather. In order to study all these magnetic activities of different temporal and spatial scales, there has been a lot of effort in numerical modelings. So to study the large scale solar cycle, we have the solar dynamo model where they use the inelastic approximation. Most of the models use the inelastic approximation and assuming the sound speed goes to infinity. So here, this dynamo model covers from the base of the convection zone all the way to about maybe 20-30 megameter below the surface, where the fluid is, where the plasma start to get to compressible. So above is about 200 megameters of distance in height, and then above this solar dynamo model, we have flux emergence model, where in this layer, in the top 20 to 30 megameter, everything gets very nasty because it's very compressible. The density drops by several orders of magnitude. Also, temperature jumps a lot in this area. So, in this area, people use flux emergence models, and they use compressible MHD model to study the rising of magnetic flux from this from the top layer of the interior region into the surface and further into the lower coronal region. And above the surface, we have the coronal model, where it studies the eruption of magnetic field in the coronal region, how the magnetic field get energized and disrupted and produces huge eruptions into the interplanetary space and might produce an effect in the Earth. So so today we will talk about both dynamo model and flux emergence model, and how it erupts in the coronal region as well. So first of all, this is a simulation produced by Yuhong's FCM code here, and this is a movie of. So the color here is showing you the strong magnetic field region with super equipotential magnetic field strength, and the color here is showing you the B5 component. So you see that this presence of the strong magnetic field bundles in the midst of magnetoconvection region here. So so you can see that in the magnetic flux rises from the bottom of the convection zone to near the surface region and has been strongly distorted by the convection motion inside the convective envelope here in our simulation. And it also produces strong, stretches the magnetic field, produces strong, long magnetic flux tubes in this region. So next, we also experiment with emergent flux tube in the Dynamo model. So we embedded magnetic flux tubes into the bottom of the simulation domain and observe its rising into the top of the domain. So here is a movie of the rising of the flux tube. You see that it kind of remains its structure at the beginning, but then it's been taken away by the convection motion, strongly distorted by the convection motion during its rising. So in order to study the emergence of magnetic flux in this tube, so we plotted the flux, the magnetic flux content in each together with the radius of the in the domain. So here is the red line is showing you the reference state. It's the magnetic flux contained in a state where there is no flux tube inserted, and the solid line is showing you the one in the north hemisphere, and the dashed line is showing you the one in the southern hemisphere. So you can basically ignore the dashed line. So the white, sorry, it doesn't show here, but the white line here is showing you the one with flux tube. So you can clearly see the magnetic flux rising through the layers from the bottom to the top. And it reaches to the top of the domain in about a month from the bottom to the top. And so later weeks, we also experimented with rising at placing our flux tube at different latitude. So this one is at 15 degrees in latitude, and we also put one in 30 degree latitude to study the emergence with respect to the latitude of the original flux tube. And so here the red line is showing you the evolution of the lower latitude one, and the white line is showing you the evolution of the higher latitude one. So you kind of see that at higher latitude, the flux tube rises faster compared to the lower latitude one, and more flux get transported to the top of the domain instead of for the lower latitude, more flux is being stored in the lower half of in the lower part of the domain. Beside that, there has also been reported of formation of coherent flux tubes forming in Dynamo simulations self-consistently. So on the left is a picture showing you a simulation by Nelson, and it with the ash code, and they formed this coherent rise in the midst of magnetic convection. And also on the right side is a simulation by the FCM code, where you see this formation of flux sheet forming near the bottom and near the top of the simulation domain. So both these flux tube that emerges to the top of the domain, and when it makes its way further to the surface, it has the possibility of forming the solar active regions here, containing sunspot. And out of the sunspot, we are more interested in the delta sunspot, where the magnetic structure are highly compressed into each other, and they produce high productivity in strong flares and CMEs, and they are observed to have strong shearing motion at the polarity inversion line together with highly sheared magnetic field lines. And and Tanaka and Lekha proposed that they can be formed by emergence of highly twisted magnetic flux tubes from the convection zone. And earlier effort has been made by Linton and Fang to study the helical kink instability of highly twisted flux tubes emerging from the interior. And recently, Toriomi, they studied a scenario of flux emergence with tube and one flux rope separately, respectively, where in the case of one flux tube, they use two buoyant sections, so they form two bipoles when they first emerge, and later on they form this nicely patched delta spot in the middle of them. While if it's a two flux rope, they form this two bipoles, and they kind of separate from each other later on. So there has been this active region 11158 being captured by SDO very well, both the magnetic field on the surface and also the coronal structure has been observed in great detail. So in this active region, there has been two bipoles, and one of them, in the middle of the active region, the two opposite polarity pass by each other and forms this highly compressed delta spot, which is very flare productive. And they actually produced an X-class flare in this area. And also the AIA image of the coronal structure shows this highly twisted magnetic field lines in the polarity inversion line area. So on the right is a nonlinear force-free extrapolated field in this region. So we calculated the study by Bastros using a flux, inserting a flux rope into a domain with convection zone and also corona. And we perturbed the flux tube in two areas so that it's buoyant in these two areas, these two segments, and they will rise subsequently after we put it into the domain. So, so here on the right is a magnetic flux. It's the total magnetic flux on the photosphere with respect to time. So, and the dashed line is showing you the free magnetic energy. So you kind of see these rising phases in the at the photosphere. So at an earlier time, 2.5 hours, you see this. They kind of rises independently with each other, forming this nice M-shaped structure. And then, as 3.5 hours, they kind of come across each other, and the emergence has been slowed down when they come they come into each other. And another hour later, at 4.5 hours, reconnection takes place at the polarity inversion line in the middle of these two opposite polarities, and they produce this highly sheared magnetic field at this polarity inversion line together with more relaxed overlying arcade structure connecting the two ending polarity in the far end. And at this point, you see a decrease in the magnetic flux with time, and also a release of magnetic free energy in this at this time. So we take a look at the magnetic field on the photosphere. So on the top is showing you the BZ component on the photosphere, with arrows showing you the horizontal component of the magnetic field. So you see that at the polarity inversion line, it's very it's highly sheared. It's almost parallel to the polarity inversion line. And also, it's not only it's highly sheared, it's also very strong. The horizontal field is also very strong. It approaches several kilogauss at the polarity inversion line here. And if we study the Lorentz force here, and on the right side, it's showing you the Lorentz force is being pushed away at the polarity inversion line, but at the two ends, they are actually being, there has been Lorentz force pushing them together and pushing these two opposite polarities together. And so we also study the shearing and rotation on this photosphere. So you see, this is also the same plot, but the arrows are showing you the velocity on the photosphere. So you see that gradually with time, there has been strong shearing motion at the polarity inversion line, and the two spots in the middle take a curvilinear path around each other, and also at the two end, in the two sunspot at the two end, we observe rotation of the sunspot here, and so this the shearing motion is also observed in the observed active region 11158. We also extrapolated the coronal magnetic field structure. So the red lines are showing you the internal coarse magnetic field of highly sheared field lines, and this green line is showing you the original one that connects the original two bipoles, and the blue line is showing you the overlying arcade of a more relaxed arcade, and which also here is a zoom-in plot of this region, and on the lower panel is showing you the nonlinear force-free field extrapolated from the observation. So you see that it compares pretty well with the extrapolated field from observation. To summarize the interior simulations of flux emergence, so we see that a rising flux tube is strongly distorted by the convection while emerging to the surface, and higher latitude flux tube emerges quicker to the surface, with lower latitude tubes remain mostly in the interior. And we see the delta sunspots by non-paired spots during the collision of two bipoles driven by the expansion of magnetic flux, and also magnetic field is highly compressed and almost parallel to the polarity inversion line in the middle of the delta sunspot. Next, I will talk about the coronal jets. So everybody here knows what coronal jet is. They are columnar ejected plasma with temperature of up to the 10 to the 5th to 10 to the 6th Kelvin. And they appear in large numbers in the coronal holes, and now the observations have shown that they are the magnetic field are untwisting during the eruption of coronal jets. And people have been proposing models of reconnection of closed flux system with an open field in the corona to study the eruption of coronal jets. So here is a movie showing you it's an AIA movie showing you the rising arcade and also the ejection of material along the jet column. So it was believed that the emergent flux into a pre-existing flux system causes the reconnection and converting magnetic energy into thermal and kinetic energy of the plasma, and produces plasma heating and dynamic events such as coronal jets. And also here is another movie, it's another AIA movie on unwinding of the jets. So we mostly focus here on the left side. So you see this, the coronal jets rising and being twisted is rotating. But when it falls back, there is actually no twisting motion. It's a straight fall back to the surface. And also, the emission is mostly in the columnar. It's in the cylindrical surface of this jet. So this simultaneous rise and rotating motion of jets suggests a common driving mechanism between the rise and rotating motion. There has been also observations of this jet-driven CME events in active region 192. So on the left, it's a difference movie of AIA image. So you see this, it's a very short movie. So you see this jet coming outward from this, from the one of the poles, the polarity, and then on the right is a Lascaux image of CME originating from the same region, together with from the same region as the left. So the President Panessa proposed this study of jet-driven CMEs. Proposed this scheme for jet-driven CMEs, where emergent mini filaments start to form in the root of one of the magnetic flux loops, and they reconnect and transfer twist to the magnetic field here, which causes eruption of CMEs. But these CMEs are of smaller scale compared with regular CME, like non-jet-driven CMEs. And so they proposed that this jet guiding and streamer-based loop was blown out by the loop's twist they got from the reconnection with this emergent field here. And to study coronal jets, there has been a lot of numerical simulations from 2D to 3D, and there have been studies on 2D flux emergence into ambient field and also 3D flux emergence into ambient field, where twist is being transferred during this reconnection here. So we also carry out our own study, 3D simulation of twisted flux rope into the ambient field here, and we want to study the eruption of the due to the reconnection of the two flux system. So on the left here is showing you the outward motion of this plasma here. So after 30 minutes, it starts to approach the coronal region and produce a reconnection here, and also outward motion of plasma. And on the right here is showing you the propagation of current. So also at about 30, after about 30 minutes, we see a propagation of current into the coronal region together with the upward motion of the plasma. So you see the current system developing at the interface here and also at the bottom of the core field here, lifting the core field up. And this is what was said by the movie. And also, so if we take a closer look at the cross-section of the simulation, so on the left side is showing you the density structure of the core, and you see that the high density stuff is being lifted up into the corona, and together with an upward motion shown by the right panel. And on the lower bottom is showing you the temperature structure in the corona. So you see that the temperature, the cold dense material has been lifted up into the eruption, into the corona during this eruption. So, and we also calculated the synthetic emission with this simulation. So at 6 AIA wavelengths, where you see the ejection of jet column and widen of this column and during the eruption. So I skip this one. And also, so we also studied the transverse motion of the jet column here. So on the right is showing you the velocity perpendicular to this plane. So reversal of the velocity sign is showing you its rotation, and because it's persistent, so it's suggesting it's rotating over there. And the rotation motion has been observed by Mark Chen in a jet event as well. So you see that this swirling spire corresponds to so you see that's this structure where the plasma has been driven into the corona and followed by a widening of the jet column. And also this swirling spire corresponds to braided magnetic field loaded with dense plasma. So next we look at the 3D structure of the magnetic fields. So on the left side, so we plotted the 3D magnetic field from the photosphere up into the corona. And on the left side, the color is showing you the magnetic twist, and the middle slide is showing you the vertical velocity, and on the right is showing you the horizontal velocity, which is we interpolate as the rotation. So on the left, so we see that on the left side of this domain, there is no magnetic twist at all, and there is a downflow in the vertical velocity, and there was no rotation at all. But on the right side, there is a high magnetic twist, and we see a upflow velocity in the vertical velocity, where it means the plasma has been ejected. And on the right side, there is a rotating motion. So we say that it suggests the gradient in the magnetic twist actually accelerates the plasma outward with apparent rotation motions, while on the left, the plasma falls down here with no magnetic twist at all and no rotating motion. And this is a study done by Yuhong and an REU student, where they calculated the emission profile in this jet column. So we see that. So you see that the plane is showing you the vertical velocity of the jet column, and the color on the lines is showing you the emission. So you see that it's a cylindrical. It's the outer shell of the jet that produces that has a strong emission, and also it's outflowing. So it matches well with the observed property of jet column. And later we did a study with the twin jet observed by AIA. So the movie here is an AIA movie showing you the eruption of a twin jet. So this is pretty early in the in time. So there has been a jet erupted from this same region, and it falls down. And after that, there are two jet rises simultaneously. So one on the left and one on the right from the same region. So on the lower right panel, it's a movie showing you the it's a panel showing you the detailed structure of this left and the twin jet, with the left jet and the jet on the right. We also did our simulation to study the production of the twin jet. So we keep running our simulation after the last time step, and then we find that it also produces this twin jet in the coronal region, where the two jets are adjacent to each other. And if we look at look at it from top, we find that the two jet actually originates from the two arm of the sigmoidal structure of the emerged field here. So so next we take a look at the 3D structure of the coronal field. It's very messy here. So the color is showing you the current density on the field lines. So the two jets are originating from the two arms, where it has been very where it's highly twisted and has a very high current density here, and so we propose that it's this field, this twisted sigmoidal structure. At the two arms, they reconnect with the ambient open field and produces the twin jet, as we observed here. So it's this two arms correspond to the two arms in the sigmoidal structure here, where there has been high current density, and reconnection takes place and produces the ejection of the two jet column in the previous emission profile. So to summarize, we find that Lorentz force resulting from the gradient of magnetic twist drives dense plasma outward, and also propagation of magnetic twist produces the rotating motion of the plasma. And thermal conduction is very important, but I didn't show that. And further reconnection between the sigmoidal magnetic structure with the ambient fields produces the observed twin jet in simulation. And so this is the take-home message. So in the interior, we studied the rising flux tube strongly distorted by the convection while emerging to the surface, and we find that higher latitude flux emerges quicker to the surface, with lower latitude flux tube remains mostly in the interior. And in active region scale domain, we find that emergence of multiple buoyant sections form a data spot during the collision of the two bipoles, and also at a smaller scale, the emergence of magnetic flux produces reconnection between two flux systems, and Lorentz force drives the plasma outwards with apparent rotating motion. And that's all. Thank you.
Thank you. I just noticed that the clock has been removed from the wall, so I assure you we have plenty of time for questions. Anybody? Ricky?
Yeah, the delta spot described as colliding bipoles, but I think when you showed the PV structure, it looked like one flux tube, right? Is that the right geometry for this thing, or it's just sort of M-shaped and it goes out and in again? Is that the geometry? It's one
flux tube,
right?
yeah.
You described, but when it intersects the surface plane, you're saying that it's the collision of two bipoles, right?
Yeah, but it's one flux tube. That's why.
This one.
Charlie.
But nevertheless, at some point, we understand that you see coronal connectivity between the two cones. So some reconnection must have happened at some time. So question: can you see that reconnectivity happening, and then once that reconnection has happened, it's more than just a single, becomes more than just a single flux tube? Or true or false?
Yeah, I understand what you're saying. Yeah. Yes. Yeah. It's kind of the test cutting reconnection takes place at the polarity inversion line, and then cuts it produces this field line, this central field line, which is kind of disconnected from the rest of from the original flux rope, the M-shaped one.
Have you destroyed that M-shaped?
It's still there. You see this, but it's just it had rotated that it's so it was an M shape, and then kind of this one goes backward and this one moves forward. So the green structure is still still looks like it's an M shape, I would say.
That reconnection, that changes the topology, is the driving energy behind strong flares in these double
Yeah.
spots?
I would think so.
Interesting flux is required for active collision. This is required. All this emergence is done.
I think for this simulation, for the ideal simulation at least, yes, because if it's without twist, they won't collide into each other, would they? I mean, at least that's what produces this strong polarity inversion line in the middle.
The one point there was just there are several ones colliding, right? If you want there, but they're not going to twist it. Oh, coherent twist.
His has convection as well. Yeah.
These delta spots appear at all phases of the solar cycle?
I don't know. I don't know.
Not during minimum.
Sure.
Scott, you know.
Yeah, I think delta spots are the most active spots. So big flares tend to come from delta spots. So I would imagine, and I don't know this for certain, but I would imagine that they're probably more prominent during high activity. So during peak of activity, I think you probably have more of these, and towards the later end of the cycle as well, because we tend to see bigger flares towards the end of the cycle. But I don't know, like, if somebody's done any kind of statistics on that. Probably
I think
somebody's
Scott has,
counted.
but
I'm sure somebody's counted sunspots before.
yeah.
The images of the jets that you showed, the one on the limb especially, so it looked like, I think just before it was later, it was on the
Oh, the one. Oh, yeah.
it looked like, I think in this one that you showed a movie, but it looked like there was a flare, like before the jet was off. Like,
Definitely.
Yes.
Do you care about that in your modeling, or are they related? Does one drive the other?
You mean could the flare be driving the jet?
Yeah.
I don't know. We didn't study the flare, but it could be. I mean, it could be that the flare is produced by the same same magnetic structure as the jet.
This one, it's actually when it's falling, it's also rotating. That's why you start with it.
Okay.
It's different from you think that.
Mm-hmm.
Yeah, it's twisting over here. It's going up. It's going yes, it's when it's falling down, it's going the other way. Okay.
It's a little hard to tell there's one on that.
Well, but it's opposite direction when it's going up.
Yeah.
It's not always going up.
It certainly looked to me like it was unwinding, because when it went up, you could see it really spinning quite long.
down. Maybe it's been back once or so, but it seems like it's not as much as
Nice. It's nice to have some Doppler velocity.
Yeah.
Sure.
Right.
Just worry about optical illusions. It sure looks like it's like, it sure does. It's like it's rotating that way, and now it looks like it flips. Yeah.
Yeah. Maybe because the magnetic twist isn't sufficient enough to,
Yes, it's obviously
yeah, if it,
twisted is just Lorentz function. The pointing function is such that it's help
Yeah,
accelerate it.
yeah,
But here, this one,
maybe,
when it's falling, it's also
maybe,
almost like it's falling along the field line.
and maybe it has untwisted sufficiently that it cannot fight against the gravity, so it's falling down.
This is in 304, so it's helium-2. We should see this at helium-1 and A30 probably pretty well. So with Chromac, once it's working and deployed, if we're lucky enough to see a flare like this, we should get good Doppler velocities. And you should really be able to tell if it's actually twisting or if you just think it is.
Or it's just falling along the field line.
Well, yeah, or
Use intensity changes that one with it.
intensity changes because you're only seeing intensity here, so you just paint it. It's a pretty wide pass band, so you're capturing everything presumably, but it's still only intensity. So actually getting an actual Doppler velocity diagnostic would be really interesting, and especially also magnetic field diagnostic. That would be even more interesting because now you know if there's some kind of in and out of the plane component of the field or not.
But Doppler velocity is sort of like the like CBS.
Oh.
Sort of, but it doesn't have the time resolution.
Yeah.
So it's just like just one frame, so it's
Right.
hard to
really tell.
Yeah.
Yeah, but Doppler, this one will just be persistent.
Yeah.
The one
Yeah.
side going towards the it is just
Yeah,
as
Yeah.
in the model.
yeah,
Yeah, that's what was seen by CBS, like red on one side, blue on the other, when it was one of these over I don't remember what it is.
Any more questions?
I think the rotation might be coming from the second one, the second eruption, and there is another eruption rising up at that moment when it's falling down. I don't know, it's the emission, so it's could be the overlapping of the two.
In your models of this evolution of flux tubes in your delta sunspot that gives rise to the delta sunspot configuration, how do your models determine things like the occurrence of reconnection? Is that determined, for example, by numerical stability?
It's by numerical diffusion.
So, for example, before the reconnection happens, then you would expect, I roughly understand that there would be a current sheet between the upcoming and downcoming, the positive and negative poles, and then that current sheet is dissipated during the reconnection. And what are the rules that determine the dissipation of the current sheet? Is it something that's in the model? Do you have control over that, or okay?
It's
So
all
you
numerical.
actually, and so now the sun itself could keep those, could keep that current sheet for some period of time, or is that true or false?
I think so. I agree with you. The sun might keep it for a longer time, but in our simulation, it gets dissipated by numerical dissipation.